So I So hi Jeff.
Hello.
Hello. Yeah, we wait for Prabha to join and others.
I hear some echoing.
Yeah. Is it okay now?
Yeah, that's better.
Yeah. Yeah, we wait for because yeah, Prabha will join later. So how the snow there?
How much snow?
Yeah.
I don't know. We have about a half a meter, maybe.
Wow. Is it the worst? The worst in this year or compared to last year?
Uh, it's maybe a bit more than last year. It's hard to know exactly what we get. I'm gonna put my hearing aids in because it's a little bit hard for me to hear you guys. Just hold on.
Okay.
Okay.
Yeah.
Jeff, good evening.
Yeah, hi.
Am I clear?
Do we want to try to share my screen at some point?
Yeah.
Okay, let's do that. I think it should be working, maybe.
Okay, full screen is on. If you could
You should-
just maybe scroll one or two pages. Yeah, okay, it works.
Excellent.
Yep.
This is good. So will you want my video to be on or to be off during the presentation?
On.
Okay.
I think we wait for another more than 5 minutes to. I think most of the people think that it will start on 9, so we wait for them.
Yeah. According to my clock, we have 9 minutes till
Yeah.
Yes.
9 o'clock.
Yeah.
So this is a 9 o'clock a.m. in Malaysia, right?
Yeah. Yeah.
So these people that are listening, are they university students or are they people in the workplace or
Yeah.
because
Mostly people in the workplace and also the student.
okay.
Yeah.
Jeff, I was just wondering about your name, your last name.
Mm-hmm.
It doesn't look very English.
It's a German origin.
Okay, all right. So you are how manyth generation in Canada?
I am actually the first generation in Canada. My family moved from the United States to Canada.
Recording in progress.
Oh, okay.
My family moved from the United States to Canada when I was 13 years old.
Okay.
Yeah, and you know, I guess it was my great grandparents who moved from Germany to the US. That would have been before 1900 even.
Wow. Okay.
Yeah.
All right. So on the what do you call it, American subcontinent, about 4 or 5 generations.
Yes.
Okay.
Yeah.
All right.
That's from my father's side. My mother's side, my mother's brother was a genealogist kind of guy, and he traced the family way back to like 700 AD.
Dang.
It's crazy. We have a family tree that's a gigantic piece of paper. It basically covers a tabletop. Yeah.
So both parents are German origin.
Or what origin?
Both parents are German origin. Or father side German, mother side something else.
Oh no, mother's side is come from England, basically.
Oh, okay.
Yeah.
Oh, that because the English, they have a good traceability with all their family. What do you call uh, the 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 plaques that they have.
Yeah, my mother's brother spent some time in England once he was retired, traveling to church graveyards and looking at the old gravestones and stuff like that. Yeah.
Oh, he really put some effort into it.
Oh, he was crazy. He spent years.
Jeff, how long you been working with Tesla? Is it from the beginning of Tesla or?
No, I started with Tesla in 2016. It was after Elon Musk announced that he was building a gigafactory in the United States. I just thought, okay, this will be the first major lithium-ion battery production in North America.
Mm-hmm.
So it would be nice to be involved with that. And fortunately, they were interested in working with me. So we've had a partnership ever since.
Mm-hmm.
Is he as crazy to work with?
You know, I don't really work with Elon Musk at all. He's you know, at a level far above the people that I
Of
work
course.
with.
Yeah.
Yeah. Everyone that I work with is really committed to the whole idea of electrified transportation and renewable energy and energy storage and all these things.
Mm-hmm.
Really a good bunch of engineers and scientists.
Yeah. For every series that we organize, I'm the one who find the suitable audience. But for your talk, I think there's a lot of group working on ion lithium batteries I think in Japan and probably in Hong Kong and Korea, also in China. But there's not a lot of group in the Southeast Asia, I think, working on this. I think you have collaborate with the A-Star Singapore, right?
Say that again. I have what?
The A-Star Institute in Singapore.
Oh yeah.
Yeah.
Well, I was in Singapore recently for the International Battery Association meeting,
Mm-hmm.
and I listened to a presentation from the A-Star people for sure.
Mm-hmm. But I think there's a company in Thailand. Do you know that they're working on? I think they're producing EV batteries.
I think there's
Yeah, in Thailand.
There's a couple of small companies in Thailand.
Yeah.
Isn't 24M in Thailand now?
Yeah.
I don't.
What do you mean?
There's a company called 24M. I think it has operations in Thailand. I don't know who's in
Yeah.
Thailand really.
There's a 4 or 5 people from Thailand who do the pre-registration for your talk. I hope
Oh, okay.
they will join this morning. Some university in Indonesia also working on this part of EV batteries. But I think it's quite active in Thailand, I think in Singapore.
Mm-hmm.
Mm.
Well, we've been very fortunate to have some visiting students that have joined us for about 1 year or 18 months from Thailand, from
Oh,
VizTech.
okay.
And they've been fantastic students. We have one at the moment. Uh, this is our 5th visitor from Thailand. They've all been fantastic students.
Mhm.
How does that work out, Jeff? How does that work out? How do you yeah, bring these students in? Is it research based or just exchange?
No, they come and do research at our place. They have a wonderful university there.
So they do research at your place means sign up for master's PhD.
No. They remain students of their own institution and spend sort of 1 year of their PhD just at our side, doing research at our side.
Oh, okay.
Okay.
Yeah. And they are really wonderful. They come from a place that's a very small university called VizTech. It has
Okay.
its only graduate student education. It's
Oh,
funded by the Thailand Oil Company. Very high, very wonderful equipment there. They basically have any kind of instrumentation you can imagine. And
Oil buys money.
students are really
Oil
good.
money.
Yeah.
do you have for the undergraduate student, yeah, that from the international student who just like an exchange student who working do some internship in your lab?
We have had undergraduate students doing internships in our labs before. Some from India, some, of course, from across Canada.
Mm-hmm.
And many times they enjoy their internships, and when they finish their undergraduate degree, they'll come for graduate school.
Okay. So I think we can start now. Probably you can, yeah.
Okay, all right.
Yeah.
I'll read off, and once I'm done, I'll pass it off to Jeff. All right. Salam sejahtera, selamat pagi, and a very good morning to all gathered here. Good evening to Prof. Jeff. Virtually, we are here for Cosmos of Curiosity, Series 28. Thank you to Dr. Nazri Halif, as well as UNIMAP Vice Chancellor Prof. Zaliman Sauli and Deputy Vice Chancellor Research and Innovation Prof. Rizal Fandi, their respective officers and broadcast control team here led by Mr. Shahrizan for hosting this event. I'm Prabha, your moderator for this CoC Series 28, formerly known as ISICS. We have changed from STEM to Curiosity. Before we begin, as is normal, I would like to introduce our esteemed speaker for this Series 28, Professor Jeff Dahn, speaking on the role of energy storage in the war on climate change. We wish you a very good evening, Prof. Dahn. Jeff Dahn, Professor of Physics and Professor of Chemistry, Department of Physics, University of Dalhousie, is a pioneering developer of the lithium-ion battery used globally in laptops, mobile phones, and electric vehicles. His recent work focuses on boosting energy density, extending battery life, and reducing costs. He has authored over 820 refereed papers and is co-inventor of 78 patented inventions. He is born in Bridgeport, Connecticut in 1957. Dahn moved to Nova Scotia in 1970. He earned his Bachelor of Science in Physics from Dalhousie University in 1978 and his PhD from University of British Columbia in 1982. He worked at the National Research Council of Canada 82 to 85 and Moli Energy 85 to 90 before joining Simon Fraser University in 90. He returned to Dalhousie in 1996 Dahn has supervised over 65 PhD students and 30 postdoctoral fellows, with 14 becoming university faculty and 7 becoming CEOs. From 96 to 2021, he taught first-year physics to more than 8,000 engineering students at Dalhousie. He has received numerous major awards, including the IBA Research Award 95, Herzberg Medal 96, ECS Battery Division Research Award 96, Fellowship of the Royal Society of Canada 2001, the CAP Medal for Excellence in Teaching 2009, the ECS Technology Award 2011, the Jaeger Award 2016, the inaugural Governor General's Innovation Award 2016, the Gerhard Herzberg Gold Medal 2017, the Killam Prize 2022, the Olin Palladium Medal 2023, and the IBA Medal of Excellence 2025. Dahn and his wife Kathy live in Halifax, Nova Scotia, near their three children, all Dalhousie graduates, and 5 grandchildren. Before I move on, very interesting years, Prof. Born in Bridgeport, Connecticut, 1957 is the year Malaysia got independence from the British.
Okay.
Okay, all right. If anyone wishes to ask anything, please do it after his talk. Hope you do not interrupt Jeff during talk. It would be better if you could type it at the chat box. Thank you. Jeff, before we begin, would you like to say anything?
No, thank you for the opportunity, and hopefully this lecture will be of value to the people listening.
Okay. Floor is
Okay,
yours.
so I'll begin.
Yep.
So when you talk about energy storage, it's important to consider the units of energy storage. What are we talking about? So we're going to be talking about electrical energy storage and other types of energy storage, and I want to use the unit of the kilowatt hour. And that's because you see it on your electricity bill. And a kilowatt hour of energy is equivalent to using a toaster for an hour. So a toaster uses a kilowatt. If you turn it on for an hour, that's a kilowatt hour. It takes a kilowatt hour of energy to raise a metric ton of water or rock 360 meters. You have to remove about a kilowatt hour of heat to freeze 10 kilograms of water. And 10 kilowatt hours of heat can heat 10 kilograms of brick to 425 degrees C. So you can store energy by freezing things or by heating them. 7 meters per second of wind passing through a 4 meter squared area for an hour can generate a kilowatt hour. And sunlight striking 4 meters squared at the Earth's surface for an hour, assuming 25% efficient solar cells, can produce a kilowatt hour. It takes about a kilowatt hour of energy to drive 5 kilometers in a typical car. And you will find that 100 milliliters of gasoline will store a kilowatt hour. You need 260 liters of hydrogen gas at standard temperature and pressure to store a kilowatt hour. And 2 liters or 4 kilograms of charged lithium-ion batteries can store a kilowatt hour of energy. So all these things are nice to keep in your mind when you consider the various ways of storing energy. So everybody agrees that fossil fuel use has to be stopped to combat global warming. And fortunately, solar and wind power are cheap and abundant, and they're being installed rapidly all over the world. But the problem is that the sun doesn't always shine and the wind doesn't always blow. So we need energy storage, and we need it big time. And what are some of the sensible options that we have? Well, one of the most simple and effective is pumped hydroelectric storage. It's very simple to understand. You have a low-level lake or reservoir, and when renewable energy is abundant, you pump water up the hill. And when you need energy at night, when there's no solar power, for example, you let the water come back down through the turbine or pump house and generate electricity. So one of the largest pumped hydro stations in the world is in Bath County in Virginia, the USA. it can store 30 gigawatt hours of electricity, and it can discharge in 24 hours. It's actually perfect for our province where I live because we use 20 gigawatt hours of electricity every day. So this system, if we had it here, would allow us to use wind power almost all the time. The efficiencies are pretty good, 70–80%, and typically the cost is the lowest of any energy storage system in the lifetime is very long. But this Bath County facility, the upper reservoir is 265 acres, and the water level changes by 110 feet between charge and discharge. And the distance between the low level and the high level reservoirs is 380 meters. And the problem is that there's limited sites like this in the world, but every single one that's available should be developed. Now, why are pumped hydro stations so huge? Like, why do you have to have so much water that's moving up and down? The reason is that you have to elevate a ton of water, a height of 360 meters, to store only 1 kilowatt hour. So to store 30 gigawatt hours, you're talking a huge mass of water that you're moving. There's other proponents that propose gravitational energy storage using man-made systems, and a company called Energy Vault proposes raising 40-ton weights up a height of 80 meters. So here you can see a frame building and the weights that are going to be moved up. So when the weights are pulled up, when renewables are abundant, and they fall down, and the cables are wrapped around a pulley that turns a generator, and you generate electricity while the weights fall down. So how much energy would one 40-ton weight store? Well, you can just use a formula from high school physics. The potential energy is the mass times the gravitational acceleration times the height the object is raised. And if you do the math, you get 9 kilowatt hours. So one of these giant weights, 40 tons, can store 9 kilowatt hours. By contrast, 45 kilograms of lithium-ion batteries can store 9 kilowatt hours. So to me, this energy storage system seems pretty dumb, and these considerations of first-year physics can help you detect when things are sort of silly. But nevertheless, this company is going ahead and installing a full-scale facility here in China. This is a 100 megawatt hour facility, and it's under construction, and it will be operating soon. Now, storing energy doesn't always have to be storing it as electricity. You know, if you're going to use it as heat, use the energy as heat, why not store it as heat? So there's a method of storing heat here in my province called electric thermal storage, and 20,000 people in my province have this, and it's pretty simple. When electricity is cheap or when renewables are abundant, you heat a stack of bricks inside an insulated box. And then when the cost of electricity is large, you blow air through the brick stack and extract the heat from the heated bricks. So this is well suited to places where renewables are supplying a lot of the energy, and you need heat in the wintertime. So does this make sense? That's the question. Well, how much energy could you store by heating 1,000 kilograms of bricks to 425 degrees C? Well, again, you go back to your high school physics and chemistry, and the amount of heat you can store is the specific heat times the mass times the temperature change. The specific heat of bricks is about 1,000 joules per kilogram per degree C. So if you take the specific heat times 1,000 kilograms times 400 degrees C temperature change, you can store 4 times 10 to the 8 joules. And if you convert this to kilowatt hours, you learn that 1,000 kilograms of bricks heated to 425 C can store 110 kilowatt hours. And 1,000 kilograms of lithium-ion batteries could store about 200 kilowatt hours. Well, I can tell you that bricks are a lot cheaper than lithium-ion batteries. So this is a situation where this makes sense. And I went down to my unit in the basement to check out, what I actually have. So my unit weighs 1,000 kilograms, and according to the website, it can store 120 kilowatt hours. So it matches our simple calculation really well. So there's been a lot of promotion about something called sand batteries. And these are situations where you have a massive amount of material that you're going to heat when the sun and the wind are abundant. And people are talking about this for even storing energy from the summertime and using it again in the wintertime. So long duration storage. So the idea is you have solar panels or wind turbines that are heating a large mass of material. And then when it's necessary to have heat, you pass water through this heated material and use it to heat buildings and so on. And there's a company called Polar Night Energy, which has these giant sand containers that are heated with renewables, and then the stored heat is extracted as needed. And what about the other direction? What about air conditioning? Well, in a place like Florida, 27% of all electricity is used for AC. In Qatar, 60 to 70% of Qatar's total electricity is used for AC. Israel, 42%. So what we need is cold storage, so that solar and wind can freeze a phase change material to deliver cooling when the sun is not shining or the wind is not blowing. And storing cold as cold would help limit the need for electrical energy storage. So it's the reverse of heat storage. And there's a company in Israel called Nostromo Ice Brick. And they make these units that can store cold, if you like. So what they have are these hollow plastic discs that are filled with water. And through this container, a heat transfer fluid is passed. So when renewables are abundant, or when electricity is cheap, you cool down these hollow plastic discs and you freeze the water inside them. And then when electricity is expensive, or it's a night when there's no solar available, you pass the heat transfer fluid through this stack of discs and you cool the water and pass it to your AC unit. So it's very simple. And if you go to their website, you can learn about the specs of these machines. One of their ice brick units, it weighs 780 kilograms. Not all of it is water. A lot of it is the container and the heat transfer fluid. But nevertheless, it can store about 12.5 kilowatt hours of energy. But if this 780 kilograms of the unit were all water, using the latent heat of fusion of water, 780 kilograms of ice can extract 72 kilowatt hours of heat when it melts. And this unit as designed is 12.5 kilowatt hours. So it's within a factor of about five or seven. And I think the device can be improved. 780 kilograms of lithium-ion batteries could store 150 kilowatt hours. So this unit is interesting, and if improved, I think it can be quite useful in the energy storage arena. What about hydrogen? Well, if you think about hydrogen made from solar or wind, you would electrolyze water to make hydrogen. That's about 70% efficient. And if you're going to store it effectively, you'll compress it, which is about 90% efficient. And if you're going to use it to power a vehicle or to generate electricity, the best way is a fuel cell, which is about 55% efficient. And if you multiply these numbers together, you get 34% efficiency to go from either solar or wind back to electricity. On the other hand, if you do battery storage and lithium-ion batteries, the charger is about 95% efficient. The battery itself is about 95% efficient. So overall, you have about 90% efficiency. So going the hydrogen route means you have to build 3 times as many solar panels, 3 times as many windmills. So it's if you think about it from the efficiency side, it just doesn't seem to be as good. But I would say that if you are set up and you do have excess electricity and there's nowhere to store it at all, well, then by all means make hydrogen in that event. Okay, so now I want to talk about battery storage. This is an overhead view of part of the Moss Landing energy storage facility in California. And every container that you see is the size of a shipping container, and each can store about 3 megawatt hours of electricity. This total facility could store 3 gigawatt hours of electricity until about 9 months ago, when a section of it with batteries from LG Chem burned up. But these kind of systems are installed all over the world, and by far they're the most implemented electrical energy storage system today. So this is for a variety of reasons, including simplicity, the smallest footprint, and cost. And I want to talk now for the rest of the presentation about lithium-ion battery energy storage. This is a really interesting graphic that appeared almost 2 years ago in the New York Times. They show how California powered itself in April of 2021. So this is sort of an average daily view of the energy mix used to generate electricity. So you can see here wind, solar, gas, imports. And then if you look in April 2024, you can see the amount of solar has gone way up compared to what it was. The amount of gas has gone way down. And you can see where the energy storage batteries have come in to help handle the evening peak demand and also a bit in the morning. So during the day when the sun is shining, these batteries are being charged, and then in the evening they're delivering back to the grid. And that's allowed the amount of fossil fuels to be dramatically reduced. And there's no reason that this can't go more and more, and it will over time. So how long do you want these batteries to last that use in energy storage systems? And if you want them to last many decades, how can you be sure that they will? So lithium-ion battery is what is used in these energy storage systems, and they're conceptually very simple. They have a positive electrode that's usually a layered transition metal oxide. And in between these metal oxygen slabs, you find lithium atoms. And the negative electrode is graphite generally. And when the lithium-ion battery is charged, lithium atoms from the transition metal oxide dissociate into ions that move through the electrolyte and electrons that move through the external circuit. And the lithium atoms end up in between the graphite layers. And the reverse happens on discharge. The lithium atoms that are within the graphite travel as ions and electrons back to the transition metal electrode. So this type of battery is very reversible, and one of the reasons is that the materials used as the positive and negative electrode only expand and contract a relatively small amount, maybe 10% for the negative electrode side. When the lithium goes in, it gets a little bit bigger, and when the lithium goes back out, it contracts to its original size. And the transition metal oxide side is a little bit smaller variation, maybe between 3 and 8%, depending on exactly what material is being used. A lot of lithium-ion batteries use lithium iron phosphate nowadays as the positive electrode, which is a very fine choice as well. So anyway, these batteries are used because they have the highest energy density, used in vehicles, phones, and tools, have a long lifetime, almost no self-discharge. They can be made in convenient sizes and shapes, for example, to fit in your phone. They're flat and thin. They're affordable, and they can be charged in a pretty short time. So I want to talk about lifetime now of lithium-ion batteries and show you that they are suitable for long-term energy storage and also for what I call what everyone calls vehicle-to-grid operation. So a lot of lithium-ion batteries use so-called NMC positive electrode materials. I forgot to mention that NMC is a lithium nickel manganese cobalt oxide material, and the relative ratios of nickel, manganese, and cobalt are given by these numbers, like 532 means 50% nickel, 30% manganese, and 20% cobalt. And typically, if you look at the positive electrode in a NMC lithium-ion battery, you'll see these sort of spherical particles. And if you look in closer, you'll see that they look to be made up of a lot of smaller subparticles. And when you look really close on a 2-micron scale bar, you can see all these primary particles that are making up this sphere. And they're configured like this for a variety of reasons. And one of them is that the lithium-ion diffusion along the grain boundaries is very fast, so that lithium can get from the electrolyte into the center of the particles very quickly. That means you can charge and discharge your battery rapidly. And for these type of NMC lithium-ion batteries, the voltage of the battery varies with the state of charge. So when it's fully charged, might be 100%. Excuse me, it might be 4.3 volts. And then as it's discharged, it might go down to 3 volts or so at the 0% state of charge level. And what battery researchers have learned over time is that the higher the voltage, the positive electrode is more reactive to the electrolyte in the cell. And that means the lifetime gets compromised the more time you spend at the highest voltages. So for electric vehicles, the upper cutoff is often restricted to 4.1 volts or thereabouts. And it's very common for both researchers and users to operate cells under restricted depth of discharge ranges. So example, you might charge from 100% to 75% or from 100% to 50% and then charge again, or some other ranges. Then I want to talk to you about the impact of the depth of discharge range on lifetime. So for an NMC 622 material, if you take a look at the way the unit cell parameters of the crystallographic lattice change with the lithium content, there are 2 crystallographic axes in the unit cell called A and C. And if you operate between fully discharged and 4.1 volts, the A-axis shrinks a little bit and the C-axis expands a little bit. So there's this sort of anisotropic expansion in the particles. And what can happen because of this is, because these NMC particles are made up of all these subparticles, and they can be aligned more or less at random, because the because the expansion is anisotropic, you can develop cracks along the grain boundaries that you see here, okay? So what is the impact of these cracks, and then ultimately, how can we avoid them? So I'm going to show you data on experiments that are based on small lithium-ion pouch cells. They look like this. It's about 4 centimeters along the direction my laser is moving. And these are machine made in China and supplied to us without electrolyte. And we fill with electrolyte in our lab in Canada. And having control over the electrolyte is a key factor in determining battery lifetime. So here's some data that's comes from a paper published a few years ago that shows the discharge capacity versus time in hours. So this graph represents about almost 3 years of testing. For NMC 622 graphite pouch cells, well, they're operating continuously at 40 degrees C and charging and discharging with a current that would cause the cell to do 100% state of charge variation in 3 hours. So that's called the 3-hour charge and a 3-hour discharge. So the black cells were operated most of the time with a 25% depth of discharge. So they're going from 4.1 volts down 25%. And the blue cells operated with 50% depth of discharge, and the red 75, and the green 100% depth of discharge. And I've listed the number of charge-discharge cycles obtained for these cells over this testing time. Now, the current that is being supplied to these cells is exactly the same for all of them. So all of them have stored and delivered the exact same amount of energy over this time period. And about every 500 charge-discharge cycles, we did a 100% state of charge checkup cycle. So for example, for these black cells, every now and then we did a 100% state of charge cycle, 100% depth of discharge cycle. So you can see that the black cells retain their capacity much, much better than the green cells do, even though that they've stored and delivered back the same amount of energy over the same time period, right? So this shallow charge-discharge cycling is much preferred to the 100% state of charge cycling. The blue is for 50% and the red is for 75%. So what this means is if you were using these in an EV, lots of short drives followed by charging is better than charging infrequently. And if these cells were used in a 400-kilometer range electric vehicle, the vehicle would have traveled 1.5 million kilometers over this time. That's a long distance, and many cars would fall apart before they travel this amount of distance. So we wanted to see what was happening inside these cells. So we did X-ray computed tomography of them at the Canadian Light Source with Toby Bond doing the measurements. And what you can see is the pouch cell, and then a zoom in, and more of a zoom in. And in this panel C, I'll describe what you see. This very bright line is the copper current collector and the negative electrode, and then the graphite layers on either side. And then you see the positive electrode with an aluminum foil current collector down the middle. And if you zoom in even more, you can see the NMC particles in the positive electrode. And what has happened to these NMC particles over this long charge-discharge cycling? Excuse me. So for a cell that's only undergone formation, no cycling, this is what the X-ray computed tomography looks like for the fresh cell. You can see the NMC particles. They look a bit blurry compared to what I showed you with an electron micrograph, but this is inside the cell, And then the cell that was cycled to 25% depth of discharge for 2.5 years, the particles look almost the same as in the control cell. But after you've been cycling at 100% depth of discharge for 2.5 years, you can see the particles have just completely been destroyed by this microcracking. It's extremely severe. And this is because the volume changes of the lattice constants are bigger when you undergo the 100% depth of discharge. You have bigger volume changes all the time, and that causes this microcracking. So it's kind of a surprise that these cells cycled at 100% depth of discharge even work, but they still work reasonably well. And this is, again, is another reason why these shallow discharge cycles are better if you want to have a longer lifetime. So we followed these cells even further than in the paper, and at room temperature, the cells undergoing this 25% depth of discharge after a charge to 4.1 have been operating for 7 years. And you can see the checkup cycles have only lost about 10% of their original capacity in the 7 years of testing. Whereas the cells undergoing 100% depth of discharge, they're dying more rapidly, but still not too bad. At 40 degrees C, it's lithium-ion batteries lose their energy, you lose lifetime more rapidly at higher temperature, but still the cell undergoing the 25% depth of discharge cycles still has only lost, 15% of its original capacity over almost 3 years continuously at 40 degrees C. If you ask the question, how far could you have driven a 400-kilometer vehicle with either of these cells? It's a very long distance, 4 million kilometers for the black cell in the left panel, and almost 2 million kilometers for the black cell in the right panel. So it's clear that charging often is much preferred compared to 100% depth of discharge cycles. So this is an article that came in Canada's most famous newspaper in 2024. EV batteries are likely to outlive the cars they power. And what I've shown you so far in the previous slide is what I would call a pretty crappy lithium-ion cell. But even these batteries are good enough to support vehicle to grid, where they're charging and discharging when the vehicle is parked. And we can make lithium-ion batteries better. I'm going to give you one example on the next few slides. And the reason for making them better is we don't want the vehicle owner to think their battery will wear out doing vehicle to grid, right? We want them to think, I can do whatever I want to the battery, and the battery is going to way outlast my car. So for those of you that aren't familiar with vehicle to grid, if any, it's very simple. You use renewables, and you can charge your car, obviously, and you can power your town or home. But at night, there's no sun. And if you have excess electricity stored in your vehicle, you can use the vehicle as a power source to power your home or your town. So the idea is that when cars are parked, they're tethered, plugged in, and they're controlled by the utility to be charged and discharged as needed to support energy storage for towns and homes. So I want to talk about one easy way to improve lithium-ion batteries, and that's to eliminate this microcracking that we've talked about already. So the upper image shows a SEM image of so-called single crystal positive electrode materials after 100 charge discharge cycles. And the lower shows an image of the standard NMC particles after 100 charge discharge cycles. Each of these particles in the upper panel is a single crystal. It's made up of one crystallographic orientation. So it just expands and contracts as a whole, and there are no grain boundaries for these microcracks to form along. So it's really incredible. And we published this paper in 2019 where we followed cells with single crystal positive electrode materials. And this is an SEM cross-section of the positive electrode. After 5,300 cycles, the cell had 97% capacity retention. And these cells were cycled over 100% depth of discharge for 5,300 cycles. And you can't see very many cracks in these particles at all. If you look at this big one here and here and here, there's some big cracks in it, but they may have been there from the beginning. Who knows? And anyway, if you use these single crystal materials and you make lithium-ion batteries with appropriate electrolytes, you can have really impressive capacity retention. So I'm showing you 20,000 cycles for cells that began testing in October of 2017. So that's coming up almost on 10 years now. And you've almost lost no capacity when you charge to 4.1 volts, a little bit more when you charge to 4.2, and a little bit more when you charge to 4.3. The reason that you would go to higher voltage is you can get larger capacity at the beginning. But these would have driven a vehicle 8 million kilometers, 8 million kilometers. So you can do 100% depth of discharge cycling and still get incredible lifetime, okay? And if there was one cycle per day to back up solar, 20,000 cycles is 55 years. So now I want to talk about vehicle to grid in detail. So there's a company in France called Ampere, which provides vehicle to grid services in France. They've partnered with Renault, and Renault uses NMC batteries in their vehicles, like I've been talking about. Two different versions, a version with a 52 kilowatt hour pack and a version with a 40 kilowatt hour pack. And these have mid-nickel NMC, so like NMC 622 and 532, which I've been talking about all the way here. And when you sign on to do this with your Renault vehicle, you have an app on your phone, which is a scheduler. It tells the minimum state of charge that you're willing to leave your vehicle in, because you have to be able to get to work or take the kids to school or whatever in the morning, and the target state of charge that you would prefer and what your departure time is going to be. And then while the vehicle to grid is operating, the EV is communicating to the grid appropriately. And all of this is just to control the charge and discharge so that you can use the car when you want, and yet the grid, the utility, can store and deliver back energy as much as it needs. And you get feedback about your session and your earnings, because when you store and deliver back energy, you get paid for doing that. This is a really interesting graph that is in one of the Ampere presentations. So here they show the percent energy retention of your vehicle battery if you're just doing driving and 20,000 kilometers per year. They say that after 10 years, you would have about 94% of the energy storage remaining. And I believe this because I've shown you that NMC batteries have incredible life. And if you're also doing this 20,000 kilometers per year and also vehicle to grid, you would pay a penalty of only 3% in 10 years. And this is assuming what they call severe vehicle to grid usage, 5 megawatt hours stored and delivered every year. Okay. So what does this mean? Okay, so 20,000 kilometers of driving per year and 5 megawatt hours per year vehicle to grid. What does this mean? Well, for 20,000 kilometers of driving, that would be only 50 equivalent full cycles, assuming 400 kilometers per full cycle. So you would do this 20,000 kilometers if you were charging and discharging frequency, it would be more than 50 cycles. But when you add up the total energy stored and delivered, it's equivalent to 50 100% state of charge cycles. So that's very little. And for vehicle to grid, if you have the 50 kilowatt hour pack, 5 megawatt hours is only 100 cycles. So over 10 years, this is only 1,500 equivalent full cycles. That's easy to do based on the test results I've showed you before. And if you were in my province and you were earning 20 cents a kilowatt hour for the 5 megawatt hours per year, you'd get $1,000 per year. Okay, so you get paid for just leaving your car plugged in. And it hardly harms the battery at all. So these are some other long test results that we've accumulated over the years. And what we have here is in the triangles and the squares. This is cells tested for 7.5 years. And the triangles and the squares are at 20 degrees C for cells charged to 4.1 or 4.2 volts. They've accumulated, where does it say this? Oh, yes. Yeah, here down in this legend, accumulated 25,000 cycles and still just under 90%. The stars are a cell that's been testing at 40 degrees C for 6 years continuously, accumulated 9,000 cycles. You know, so vehicle to grid is no problem. 1,500 cycles, 10 years of vehicle to grid is trivial for cells with single crystal positive electrodes. That should say positive, not negative. And even the crappy lithium-ion cell that I showed you at the beginning can do 3,000 cycles at 100% state of charge at 40 degrees C. And you only need 1,500 for 10 years of vehicle to grid and driving, right? So this is easy, even if the cell was at 40 degrees the whole time. And if you operate at 25% state of charge cycling, you can do over 10,000 equivalent full cycles, you know. So I think vehicle to grid is compatible with most batteries that are in vehicles today. So here's some very interesting data, feedback from the field, 6 months of customer usage. So here what they're plotting is a graph of the frequency of vehicle to grid sessions and how long they were. So you can see the peak in this distribution is around 12 hours. And that makes sense because a lot of people would plug their car in when they get home from work and then unplug it when they go to work the next day, because a lot of people don't have the ability to be plugged in at work. But it's really interesting. There's one person that was plugged in for over 800 hours without driving in the you know, so he must have been gone on a trip or something, right? And then they have this graph here showing the cumulative vehicle to energy use per vehicle. So each one of these dots represents a vehicle for 6 months of use. And if you sort of look at this, you say, okay, so some of these guys charged 500 kilowatt hours or half a megawatt hour and discharged back 400. And some of them were doing almost 1.5 megawatt hours and discharging back 800 kilowatt hours. So you kind of put a star at the average, or where it looks like maybe the center of all these dots would be. That's about a half a megawatt hour being stored and delivered back in 6 months. So to make things simple, we'll say on the average, these vehicles could store and deliver about a megawatt hour per year. And in my province, that would be about $230 that you could store, that you could make doing this. But as people become familiar with this, they'll learn how to optimize use to move further down the graph. to earn more money. The city of Utrecht in the Netherlands has a large vehicle-to-grid operation going on. There's over 500 AC bidirectional charging points that are installed where you can park your car during the day and leave it tethered and have it operate in vehicle-to-grid. This has reduced peak electricity demand by 20%, and the business models provide benefit to the owners and the grid operators. And there's a lot of vehicles involved in this. I forget the exact number, but the order of 500 to 1,000 vehicles are involved at the moment. This is a really interesting graph. It shows U.S. electricity consumption from 1990 to 2026. So electricity was going up and up and up, and then conservation became recognized as being very important. Heat pumps came available, and electricity usage more or less flattened out. But now it's going up again, primarily because of all these AI data centers. And the U.S. electricity consumption is about 45 terawatt hours in a year, okay? 45 terawatt hours. Well, we've just seen that one EV doing vehicle to grid can easily store and deliver a megawatt hour per year, right? So 1 million EVs doing vehicle to grid could store and deliver a terawatt hour per year, right? So that's interesting. That's would help you combat this rise from data centers. And according to a recent report, in 2024, there were 4 million electric vehicles in the US at that time. So if you only had a quarter of them doing vehicle to grid, you could store and deliver a terawatt hour. So you can deploy more solar and wind and meet this energy demand that you see here. And as electric vehicles become more and more prolific, using vehicle to grid just makes more and more sense. South Australia is a very interesting place because 70% of South Australia's energy comes from solar and wind. It might even be more by now. And because of this, you'll find that electricity costs are negative from time to time. In fact, in 2021 and 2022, about almost 20% of the time, electricity prices were negative. And this is when there's excess grid scale solar and wind, okay? And so what this means is it makes sense to have your vehicles plugged in when electricity prices are negative, because the utility will pay you to store that electricity and then deliver it back when electricity prices are positive. So in South Australia, they're mobilizing to make virtual power plants of grid-tied cars. And they're clearly a lot smarter than North Americans because we are very far behind in this particular situation. In California, Tesla Powerwall owners can connect their home energy storage unit to the grid and allow their home energy storage unit to be charged and discharged as necessary to store excess solar and then deliver it back at night. And this was an article that said Tesla Powerwall owners earned nearly 10 million through virtual power plants in 2024. So that's all the Powerwall owners together, not one particular person. So this one person earned $800 in that year. And there's no difference between this and vehicle to grid. The only difference is the battery in the vehicle to grid can move when the car is driving and it's not plugged in. And then finally, this is an interesting story. So there's a very famous company called Redwood Materials, which was formed to recycle used electric vehicle batteries and extract the nickel, manganese, cobalt, lithium, aluminum graphite from them, aluminum and copper from them. And as these vehicle batteries were being turned in, they were realizing a lot of them still had a lot of useful life. So they formed a new company called Redwood Energy, which is deploying used EV batteries to form energy storage systems, right? And it's very clear that when I'm showing you the lifetime of the batteries that EVs are going to have, even if they do vehicle to grid for 10 years or even 15 years, by the time the car is falling apart, the battery is still going to be useful. So put it into second use, okay? And that's what people are doing now. So I'm done. I just want to summarize. The use of fossil fuels has really messed up the earth. You know, global warming is a real problem. And we need to stop burning fossil fuels as quickly as possible. And the use of renewable energy sources means that we need energy storage. And some sensible options are pumped hydro, the sites are limited, heat storage, stores heat when you're going to use it as heat, cold storage, stores cold when you're going to use it as cold, and battery storage is the largest deployed option. And I think that vehicle to grid and second life of EV batteries is going to play a huge role, right? Because the batteries can handle it. And the longer the batteries last, the better. And we have a large effort in our laboratory on improving battery lifetime in the multi-decade scale. And this is it's a huge challenge because how do you test something for 50 years to prove it will last 50 years? You have to have, you know, very good confidence in your lifetime predictions. And that's what we're trying to learn how to do. Okay, so I'm finished. And if there's any question period, I'd be happy to try to answer questions. So I'm going to stop sharing now.
Okay. Thank you, Jeff. That was quite an eye opener. I really didn't think of vehicle to grid. It's actually equivalent to what we are doing right now: solar to battery and battery back to the grid. It's a similar thing. Only thing it's a moving battery now.
Well, it's not moving when it's actually connected to the grid.
Yeah, correct. Yeah, yeah. So that's quite an interesting concept. Before we open up, I'd like to ask a few questions. How difficult is it to produce the single crystals compared to the polycrystals?
It's very, very simple. It typically involves heating. During the heating process where you're making the NMC, you would heat only about 50 degrees centigrade hotter. And it tends to lead to about a 3% cost premium over the standard NMC.
Oh, okay. So it's quite a simple process.
They're mass produced in China. Huge quantities of single crystal materials are being made now.
Okay. And on when you compare fossil fuels and lithium-ion batteries, how much how should I say it? How much damage are we looking at on the production side, on the synthesis of the materials? How much are we wasting? How much when you compare those things?
Yeah, so this is a tough question to answer, but I'll try to do it as simply as I can. So it's been shown that approximately the amount of energy that you can store and deliver in 50 charge discharge cycles of a lithium ion battery is the amount of energy that it needs to make that battery. Okay. So to make a lithium ion battery, you'll get that back if you charge and discharge it only 50 times. So if the battery can last 5,000 cycles, it's a factor of 100, right?
Yeah.
It can last 10,000 cycles is a factor of 200. And then you step back and say, well, what if we're using renewables for that energy, not fossil fuels? Okay, then it's win, 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 right? And the other thing that I like to point out is we are spoiled by oil. You dig a hole in the ground and oil comes out. That's just amazing, okay? But the consequences are not good, right? Yeah.
Like, you just dig and it comes out.
Well, I mean, that's what happened in the beginning, right? When oil was discovered at the beginning, it was dig a hole and this black stuff comes out.
I, I would like to share a simple anecdote I heard from one of my Palestinian friends. They really don't like Libyans. Palestinians don't like Libyans. They said, Libyans, you guys just take a shovel and dig anywhere on your earth and you get oil flowing out.
Yeah.
Okay. On the when you say a 50% charge cycle, that means let's say on a handphone, that means you're going to use it to 70 or 60% and then charge it up to 80%.
Well, if it's a 50% cycle, let's just say you charge to 70 and discharge to 20.
Okay,
That would be
charge to
50%.
17. Okay.
Right. So with my electric vehicle, my wife and I typically charge to 70, and then when it gets down to like 50, we'll plug it in.
Okay.
Because we know short cycles are better.
Okay.
But of course, if we're going on a long trip, we don't hesitate to charge to 100 and go all the way down to 20 because we don't do that frequently, right?
Okay. All right. I think I've seen my Apple phone highlighting that to me. He says, okay, I'm going to stop around 80, 85%, and it slows down the charging after that. It takes longer to charge, yeah. So the Apple phone, I think they realized this then, and they optimizing the charge to, like what you say, 50% charge.
Yeah, like my phone is an Apple phone here, and it has a ability to charge to 80%. So for me, I'm not a real heavy phone user. So if I charge to 80, by the end of the night, I'm down to, I mean, by bedtime, I'm down to about 50. So only like 30%, right? So I don't need to charge 100%.
Yeah. Okay, in the questions, Jeff, if you had to choose which one, longer cycle life or faster charging, which is more realistic to improve significantly in the next decade?
Well, some people really want faster charge, and those are the people that really don't have the ability to plug in at home. Okay, so they don't have a home charger. So somebody like me with a level 2 charger at my house, we've charged at a public charger in the last 3 years. We had our vehicle for 3 years. We charged at a public charger once. Okay, so for us, fast charge is irrelevant. And for a lot of EV users, fast charge is irrelevant. But when you're on trips and you have to charge, then fast charge is nice. Now, if you're talking about energy storage batteries, so the type that don't move around in cars that are being deployed everywhere, those aren't charged fast ever. And in that case, lifetime is the most important thing you could ever do. Longer and longer lifetime. There's an article just came out about 10 days ago where the authors examined solar cell performance for cells that have been in the field for 30 years, okay? And they were astounded by the fact that the degradation rates were about 4 times less than people had been saying, okay, 1% per year degradation. Way less, like 0.16% per year. Like these panels are going to last so long. It's fantastic.
Mm.
These are silicon solar cells that are all these cells were in Switzerland, you know. So the batteries should match the solar for sure.
Mm.
You know, that's what we have to do. I
Mm.
think they're both important. Fast charge really important for one segment, and long lifetime really important for another.
Yeah.
Okay.
Bravo. I think,
Yeah.
that's my question actually.
Yeah.
Jeff, people want to change from, you use petrol and then you use batteries. That make people think about how fast you can do charging. The time that you spend to fill up the fuel and the time you spend to charge. That's what most of my friends who are using EV, they think about the transition of the culture of the energy.
Let me turn this around for you,
Yeah.
okay? If you were an EV owner like me, you'd be saying, my God, if I have to go to gas, I have to go to the gas station, pump that smelly shit into my car. That's so inconvenient. As an EV owner, when I get home, I just take my charger from the wall of the house, move it 4 feet, and plug it into the charging port. It literally takes me 20 seconds. Okay. I don't want to go to the gas station and waste that time and deal with that smelly stuff. Right. So once you've experienced EV, you're never going to go back. Better car. It's more, maintenance costs are almost zero because you don't have oil changes, you don't have transmission fluid, you don't have all this stuff. And you hardly ever use the brakes because you have regenerative braking. So it's just an amazing thing. Really amazing.
What's your average speed like, Jeff?
My average speed?
Yeah.
Depends. If you're on the highway, you can go 120, if you want to go 120K, it's no problem. If you want to go more, you can too.
Okay.
These cars have a lot of juice. They really go.
All right. Okay, Jeff. So what you're saying, fast charging, I suspect the fast charging is actually a temperature issue. So it causes degradation of the unit cells.
Well, not really. So most electric vehicles, when you want a fast charge, the battery packs are heated. Okay, so that you improve all the kinetics, the diffusion of the lithium ions in the electrolyte and the solids all improve at higher temperature, and you can charge faster.
Yeah.
And this is a exposure to high temperature like 60 degrees C for half an hour or so during the fast charge process. So it doesn't harm the battery in the long term really at all. And fast charging in the winter, it's exactly the same. The packs get heated so that they can handle the higher currents.
Okay, so it's quite different then. On a comparison note, how do you compare a lithium-ion battery to a classical lead acid?
Well, energy density is way, way better. Probably, you can store the same energy in 1/5, no, even like 1/8 of the weight and 1/3 the size.
Okay.
And the cycle life is way longer. The only thing that's an advantage for lead acid is the cost is a bit lower, right? But they're heavy.
Heavy, yeah.
They're
Constant
they
topping
don't
up
do well
maintenance.
at very elevated temperatures like 50 and 60 degrees C. They don't like that at all. So lithium ion is the way to go.
But what about current density?
Well, current density, lead acid uses an aqueous electrolyte.
Yeah.
So the current densities can be much higher.
Yeah.
And what that means is the electrodes are made thicker so that you don't have as large area electrodes. What lithium ion people have done to combat that issue is to make very thin electrodes with large area.
Okay.
So the current densities are
comparable.
Maybe 20 times smaller, but the C rates, the rate of charge and discharge is the same.
A question, how much can recycling actually reduce future resource pressure?
Well, everything you recycle means something you don't have to dig out of the ground. So recycling is important, and many, many companies around the world have worked on lithium battery recycling and have developed methodologies to do it. The only slightly worrisome thing about recycling is the big growth in lithium iron phosphate lithium ion batteries, because there the positive electrode is iron based, and the amount of value you get recycling a lithium iron phosphate battery is lower, to the point where it's maybe not even economically viable to recycle them. So in such a situation, you have to say, well, these things are proliferating everywhere, and we can't have them just piling up in a mountain when they eventually die.
Yeah.
So it's kind of like, it's like tires. When you buy a tire, you pay a tire recycling fee, at least here in North America you do, to make it economically viable for the tire recycler to do it. And that's what I think has to happen for lithium iron phosphate batteries, is that either the manufacturer or the purchaser has to say, yes, I have to put money in that will be used eventually to pay the recycler of this thing.
Okay. What is the hardest battery problem that cannot be solved by better engineering alone?
Well, there's a number. So let's talk about low temperature performance. So if you want any battery to operate, let's just say at minus 50 degrees C, that's tough. Not impossible, but the battery you will make will not function very well at 40 degrees C. So very wide temperature range is pretty difficult. And then there's a situation like, okay, say you want enormous energy density, 1,000 watt-hours per kilogram, instead of the typical 300 nowadays with state-of-the-art lithium ion, or 350. That's like, you need a new periodic table for that. So engineering's not going to get there. So super high energy density, super wide temperature range, these are very, very tough.
Okay. The next one is what do battery researchers still not know but often pretend to understand?
Oh, hell. This is great. So there's okay, so how does a lithium ion battery work in the first place? Well, I made a simple description in the lecture. But when lithium goes into the graphite, that material becomes almost as reactive as lithium metal. And lithium metal reacts with everything, including the electrolyte in the lithium ion cell. Okay, so the lithium containing graphite reacts with the electrolyte in the cell. And you would say, well, the thing should just not work. But it turns out that the reaction products form a layer on the surface of the lithium intercalated graphite. We call it the solid electrolyte interface, okay? And this solid electrolyte interface is absolutely key in understanding the lifetime. You have to make this interface really, really robust to allow the cell to operate. The lithium has to transfer through it and prevent all these reactions with the electrolyte. But its actual composition and the way it works, its chemical and structural makeup is, I would still say, mostly a mystery. And yet, many lithium ion battery guys, not me, will say, oh yeah, we understand this thing really well, you know, blah, blah, blah. Okay, but in actual fact, they don't.
Okay, that
So-
reminds me, Jeff. That reminds me in your micrographs, I noticed that all the crystallites, I mean, sorry, all the grains of different sizes. Would growing them or making them equal sizes somehow affect the battery capacity or the voltage?
No, they won't affect the voltage or the capacity, but um, there's a researcher in Korea named YK Sun, and he's done a lot of work on these polycrystalline materials, not the single crystal ones. And what he's shown is that if you, how do I get my hand in here?
Yeah.
Each of my fingers is a crystallite, and they're all aligned so that the two crystal axes are all in the same directions.
Okay.
Then you can reduce the propensity for this microcracking.
Okay.
Okay, so there is a way to engineer these polycrystalline particles to make them better, but they still can't compete with single crystal.
And about the grain sizes, the different grain sizes?
Yeah, so if you make the grains too big, then the distance the lithium has to transport through the material to get to the center becomes large. And because that's a diffusion process, it takes greater time.
Okay.
So that means that the ability to fast charge and fast discharge becomes less. So you have to keep the particles in the grains relatively small to maintain this ability to charge and discharge fast.
Is in that sense, is there any active work on nanocrystals?
Well, again, as you go super small, there's other problems that come about, and one of them is the specific surface area becomes
Yeah.
larger. So,
Yeah.
right, because small particles,
Yeah.
you end up with more surface area. That
volume,
means more
volume to area.
more area of contact between the particle and the electrolyte, which react with one another and form this solid electrolyte interface. And you really want to minimize that area of contact. So you're sort of in a range where there's a sort of a sweet spot in
Sweet spot,
size,
yeah.
not too small, not too big. Yeah.
So we have not reached there yet. Okay, there is a question by Kyrol, my EVOC. I don't know what's my EVOC. What other battery chemistry that have potential under research? We have solid state batteries, sodium ion, lithium sulfur. Any other notable chemistries?
Yeah, all of those are lithium and sodium based, and there's a fair amount of work going on in the world now on alternatives that are water based systems. So things like rechargeable zinc manganese dioxide and other aqueous systems, just because the all the batteries that were described in the question, they all have the propensity for safety issues. Okay, even solid state, people say, oh yeah, solid state is safe, but solid state is interesting because there is no ability in a short circuit situation for the cell to stop discharging. And that means it will just, all its electrical energy will be dissipated inside as heat. And people have shown that the temperatures go up to like 1500, 1700 degrees C. So they're just China syndrome right out of whatever device they're in. So water-based systems have this advantage of, more inherent safety. Now that's, lithium ion batteries have a fantastic safety record, but there's just so many of them out there that every now and then you hear of an incident in a vehicle or a phone or an energy storage system or whatever. But the frequency based on the number of batteries is incredibly low.
Yeah.
It would be better if it was absolutely zero. Yeah.
Okay, where was it? Okay. All right, Jeff, do you see a post-lithium era for EVs, or lithium ion will dominate longer than people expect?
How long do people expect? You know, that's the question. I mean, what's going to replace lithium ion in vehicle? So let's talk about that for a minute. What are the options? Well, sodium ion, energy density of sodium ion is less than lithium ion, even less than lithium iron phosphate. Okay. And if you want a really short range vehicle, maybe you would use sodium ion. But lithium iron phosphate is really inexpensive too. And can sodium ion compete in price with lithium iron phosphate, lithium ion? Not clear. Depends on the lithium price. Right now, the lithium price is high, and the price of lithium iron phosphate batteries has risen from about $45 per kilowatt hour up to 65 just in the last few months. Okay. Wow. And you know, when the lithium prices are high, then sodium ion can compete on price. But it's not ever going to compete. Well, we can't say that. At the moment, it's unclear how it can compete on energy density, right? So sodium ion has a place, I guess.
On that, sorry,
Yeah,
carry on.
I was going to talk about solid state.
Mm.
You know, solid state gets better and better all the time. And you go to conferences and you're just, gee, this is getting better, right? Really getting better. But almost every time it's getting more complicated because you have to have the interface between the electrode materials and the solid electrolyte has to withstand volume changes and also the chemical reactivity between the solid electrolyte and the electrolyte. So they have coatings on particles, and every interface has a coating layer, and you have to operate them with a relatively high physical pressure. And can they compete on cost? That's the question. I don't know whether that's clear yet. And lithium ion keeps getting better. Energy densities increase, cost goes down. You know, it's like trying to replace the silicon solar cell, which is manufactured at scale, works really well with a new technology. It's really tough to come in when you're not making things at scale and trying to compete with something made at scale. Lithium sulfur, you know, it's been worked on for 50 years and still has a lot of problems. So it's not clear to me what will replace lithium ion in the next 15, 20 years. Not clear.
On that note, Jeff, I'm not familiar with lithium. So, is there enough lithium to be mined?
It depends who you talk to. I think the answer is yes.
Okay.
Yeah.
To last us 200, 500,000 years. But that also means technology improves, that we would be able to eventually recycle lithium.
Oh yeah.
Yeah.
Oh, the recycling it can be done. You know, there's a local company here called Lab 4 in the province. You know, they have this really slick process to extract everything: cobalt, nickel, manganese, copper, aluminum, lithium. They all end up in a separate container as this liquid flows through these columns, extracting out the different elements. It's just nuts. You just say, wow, does this really work? Oh yeah, it works great. Okay. And it does. It's fantastic.
Okay. So as price goes up, recycling would be the, so right now we'll be,
you know, it's not about economics. It's about, you have to do what's right.
Yeah, correct.
We recycle aluminum pop cans, right? Yeah. Because it's the right thing to do. Also, it's economically valuable, but you know, we recycle tires, and you know, here we have waste streams for all the paper goes in one waste stream and all the plastics go in another, and they all get recycled, right?
So it's about time to do the right thing then. Azarul. Hi Jeff, very interesting sharing on EV. I have a question on battery safety. Is it true that NMC is not so safe compared to LFP in terms of battery thermal runaway?
Well, if you subject an LFP battery and an NMC battery of the same amp hour capacity to the same electrical and mechanical abuse scenario, the LFP battery will be less likely to go into thermal runaway than the NMC battery, okay? But that scenario of electrical and mechanical abuse is rarely found in real operation. You know, this is why there's very few EV fires. There's very few phone fires. I mean, phones used to catch on fire quite often, but now it's incredibly rare, right? And there's been a lot of advances that have made this possible. One of them is the ceramic coated polymer separator that's used in lithium ion cells today. You know, in the old days, the separators were microporous polyethylene or polypropylene. And when the cells got hot, these things would just melt and flow, and then you have a really bad situation. But when you coat them with a ceramic layer, just a couple microns thick of aluminum oxide, that gives them dimensional stability, and it prevents this type of issues. So the ceramic coated separator is used virtually in every EV battery today, and in most batteries actually in power tools and whatever. And it's, you know, improved the safety a lot of LFP and NMC for sure. Oh, and one other thing. This is interesting. Okay, so you just said LFP batteries are safer. All right, good. Let's make them bigger so that we don't have to make so many interconnections between the cells that we put in our pack. Oh, they're still safe. Well, let's make them bigger. So now LFP batteries are like 1,000, they can be 1,000 amp hours, one cell.
Wow.
There's a company that makes a LFP battery called Mr. Giant, 600 amp hours, okay? And as you make them bigger, you know, any kind of thermal event, it's just hard to get the heat out just because it's big, right? So you go from a situation where you literally are, you know, quite a bit safer, but then as you make them bigger and bigger and bigger, you end up, you know, marginalizing that advantage.
Okay. So that makes sense why EV batteries are always compartmentalized in slats.
Yeah, modules.
Yeah, modules. Yeah, for thermal management.
Yeah.
Okay. Nazri again. Is China more willing to deploy good enough battery tech at scale while the West waits for perfection?
You know, I think that Chinese lithium-ion batteries from the tier 1 makers, they're excellent, truly excellent. And so are the batteries from the tier 1s from Korea and Japan and so on. And all these are being deployed in various jurisdictions around the world. But then again, there are, you know, battery makers that aren't quite such high quality, and those batteries get deployed here and there as well. So you have to be careful about which batteries you select if you want really good ones.
Jeff, you keep saying battery manufacturing, China, Japan, Korea. What about Europe? What about North America, South America?
There's very little manufacturing going on so far.
The reason being?
Well, what is the reason actually? Well, nowadays in North America, there are some plants that have been established. So LG Chem has a few plants, and SK has a few plants in the US. Tesla has some plants in the US. I'm not aware of anything in South America. There may be. Europe, there's a few small plants that are coming online. The real situation is the lithium-ion battery mass production started in Japan, and the Japanese became very good at it and did really well. And then it spread to Korea, and the Koreans picked it up and became very good at it. And then it went to China, and the Chinese just, they produce like 90% of lithium-ion batteries today, and they're very, very good at it. Very good. Excellent cells, a fantastic, huge research infrastructure in the universities and so on. It's just a gigantic, successful effort.
You are describing lithium technology travel like COVID-19 virus travel from Japan to Korea to China. Okay. Where's this? Khairul, what are you looking forward to, Jeff, in 2026 in terms of lithium battery or in general terms?
I'll give you two perspectives. One is as a researcher. In our laboratory, we have about 40 people, and we like to be excited by what we do. And we talk about something called blood flow. When you see a new result that gets you excited, it makes your blood flow. So in 2026, I want to have a lot of blood flow. Okay, that's and then outside of the laboratory, what I want to see is I want to walk down my street and I want to see an EV in every driveway. Okay. And we're getting closer to that. There's my neighbor on one side has an EV. We have an EV. There's another EV on the other side of the street, but I want to see the whole street, EVs everywhere. Maybe that'll take 10 years. Okay. The sooner the better. And I'll be happy.
On that note, Jeff, how because I don't get much news on the resistance of the oil giants to EV. How is it going on in North America? But okay, I must say this, that over the time over here, even in Malaysia, a lot of petroleum companies have shifted from oil as a fuel to petroleum for plastics. So that shift has been going on for the past 5 to 10 years, and more investment on there. But how resistant, how pliable are they towards EV?
I think a lot of it comes down to the attitude of the EV buyer, not necessarily the big companies. So, the United States has unfortunately taken a giant step backwards with the current administration that don't even believe in climate change, right? It's really quite sad. But some states like California, so California in 2025, there were more new EVs sold than new gas cars in 2025. So that's really impressive and moving in the right direction. In Norway, it's been like that for several years. Like, I think something like 80% or 90% of new cars last year were all electric in Norway. So certain jurisdictions of the world get it, and they're doing it. But other jurisdictions in the world, and not helped by the people in power at the time, unfortunately, in some cases.
Okay, so it's people management. not so much
Yeah.
technology.
You know, in Canada, just a couple weeks ago, our government made a trade deal with China because China was putting large tariffs on some of our agricultural products and seafood products, and the deal was lower those tariffs and we'll allow Chinese electric vehicles into Canada. So I think that's really good. You know, now, um, you know, consumers will have access to these really nice Chinese vehicles that are lower priced. And, you know, I find it really kind of funny because everybody's so upset in the US and North America. You know, what about these Chinese vehicles? What are they going to do? Well, go out in the street and look around. Over 50% of the vehicles on the road are from Korea and Japan,
Yeah, yeah,
right?
yeah.
Like, give me a break. And no one talks about that anymore. It's just the way it is. And it's partly because they've all established manufacturing plants locally in North America. And if you give the Chinese companies the chance, they will do it too.
Okay.
Yeah.
Since you brought that point up, how good are the Chinese EVs compared to Western EVs
Oh,
in terms of drivability, in terms of comfort, longevity?
you know, I've never driven in one, but there's a lot of reports out there about the cars that BYD makes, for example. They're just excellent reports, and they're being imported in great numbers in Germany now, and with great success. I think the cars are good. I think they're good. You know, the major makers make good cars.
Oh, since you mentioned Germany, I was wondering about this. Why aren't the traditional vehicle manufacturers really jumping into the EV bandwagon? They seem to be reluctant. Of course, we see more of them coming out, but not in the numbers that China is doing. Why is that?
You could ask the same question about North American vehicle makers
Yeah,
too.
yeah, true.
And
Yeah,
the
yeah, true.
answer is at the moment it's more profitable for them to keep making gas vehicles. So,
So it's a money issue.
well, a lot of it is a money issue. You know, they trying to make a profit and stay competitive so they can make more money with gas vehicles at the moment.
So
But, you know, Volkswagen, Porsche, BMW, they all have very nice electric vehicles.
yes, they do. Yeah, yeah.
Yeah.
I heard they're more comfortable and less rickety than Tesla.
Tesla makes very nice vehicles too.
All right. Electronic Materials Group. What do you think about the potential application of high voltage LIB using lithium nickel phosphate and lithium cobalt phosphate in the near future?
Well, that's
Changing
easy to answer. Zero. Zero probability of success. The reason is the voltage is so high that there's no standard liquid electrolyte that can handle this. No way. The reactions between the positive material and the electrolyte at those voltages, 4.7 volts and above, it's just impossible to handle for a long lifetime battery. You know, you could make something that lasts 100 cycles or whatever, but what's the point?
Okay. I think that's about what we have for you.
Okay. Well, been a good conversation anyway. That's cool.
I hope you enjoyed as much as we did.
Yeah.
Okay. Before we bid you good night, Jeff, we'd like to have a photograph with everybody. Snapshot. Could everybody please switch on your cameras, please?
I wonder if
Cameras,
I'll
please.
recognize anybody.
Cameras, please. Okay, cameras, please. Cameras, cameras, cameras. Okay, nice. Cameras, please. Shah, whenever you're ready. Shah.
Okay, done, Prof.
Okay, all right, thank you. All right, thanks, Prof.
Thank you,
Jeff.
Prof. Thank you.
Okay,
Thanks,
bye-bye,
Jeff.
everyone.
Yeah, bye-bye. Thanks.
Thank you and good night, Jeff. It was very, very nice having a conversation with you. Hope you'd join us for future sessions too.
Okay. Okay, good.
Debate
Good night and
sessions. All
good
right.
morning.
Good night. Good
Bye-bye.
night. Good morning. Thank you. Bye. 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 All right. For the rest of you, you can stay on, get your online set. Where's the QR, Shah? QR tak keluar lagi. Mr. Khairul, my EVOC dari mana?
We're the Malaysian EV Owners Group.
Oh, okay.